Welcome to another RDWorks Learning Lab. Again, I've taken the opportunity to start this session off in the warm because it's a bit cold out there. But we need to be in the office to start with because I want to show you some rather interesting video. Today's subject is a very misunderstood subject. And to be honest, I'm a little frustrated at watching some people's video trying to explain what happens and how and why you should use air assist, how much pressure you should use, when you should use it, why you should use it, and how it works. Now in this session, I'm going to get to the bottom of all those questions. But let me warn you, this is going to be a 4-year PhD in physics session done in about 5 minutes, with little images which will help you understand what's going on. And you don't need letters after your name to understand this stuff, but a lot of it will be new to many people. So for the scientists amongst you, I apologise, because I'm not a scientist, I'm an engineer, and I like things in a very simple pictorial form so that I can put the pieces together like a jigsaw puzzle. Now that's a very good analogy because air assist is basically the picture on the box. What's inside the box is hundreds of pieces that go to make up air assist. It isn't just one subject. Hold on to your hats, get yourself a strong cup of coffee, and let's get going. So what I'm going to show you first of all is a step through at 20 millisecond intervals of a pulse hitting a piece of, in this case, 1/2 inch MDF. And then we'll move on to a piece of 1/2 inch poplar plywood. Two different materials, the same pulse. In this first image, the pulse is only 10 milliseconds long. So let's take a look at what happens when the laser beam hits the wood. A laser beam is invisible. So why are we seeing a white splash? Let's step on. Now you'll observe, because of the lighting, the effect of the smoke coming up here. Look, it's coming up like a little volcano, and producing a mushroom cloud well away from the work. And look what's happening to our whatever it is that's happening here. Now the pulse is virtually finished. And look where the smoke is. The smoke is up here. Remember, it went up like this, and it's ballooning out just up here around the nozzle. And then we'll go to probably the last frame in the burn, and you can see where the smoke is. Here and here. It's like a candle being snuffed out. That was a piece of MDF. MDF is not wood. It's a mixture of wood and a plastic binder. Let's move on to a piece of wood now. As you can see, this is plywood. This is very soft poplar plywood. This is just pure wood and no plastic involved. The pulse will actually burn a lot deeper in this material. Again, what's this white stuff here? Because the laser beam has got no visible light. It's an invisible beam. And again, we'll take a look here and we'll see our smoke billowing up like a little volcano and collecting at the top here. Let's push on and watch the smoke particularly. You see the way that it's puffed up? And look, here is our little jet of smoke after the event. There's a huge amount going on in those images, which most people have never bothered to look at or watch or even understand. That's the basis for our first look at some science. Okay, we're going to come at this subject quite gently from a point of view of things that you already know. I'm sure you understand how sound waves work. So these pulses of energy hit your eardrum and make it vibrate. 20 cycles a second, up to about 20,000 cycles a second. Now that typically is the range of frequency that you can hear. Look, these are still waves, but this time they are light waves, not sound waves. Now, this is something called an electromagnetic spectrum, because these are electromagnetic waves. Now, they do the same thing as sound waves. They hit things and then make them vibrate. we've got a range that we can see in this spectrum. It's this colour range here. Look, all the colours of the rainbow. That's because we've got sensors in the back of our eye which are only sensitive to this range of frequencies. Outside this range of frequencies, we cannot see what's happening elsewhere. We can't see X-rays, we can't see microwaves, we can't see phone signals or radio waves or TV signals. The wavelength that we're going to be working with is 10.6 microns. Now, in this range that we are going to be using for our machine, our audible hearing is 20,000 cycles a second, and yet here we are at over 1 trillion cycles a second. And that's what our eyes are capable of perceiving. There are some very interesting properties that happen in this region here. So we've gone from sound to light, and now we're going to go to material. I think everybody knows what that is a picture of, an atom. Isn't Google wonderful? Because all of a sudden we can very quickly show you, without any of my dodgy diagrams, something that's very easy for me to explain. These are individual atoms in a very diagrammatic format that most people will recognise. I mean, they don't actually look like this at all, but it's a way of describing them. Now look, this is H2O. It's got 2 hydrogen atoms attached to an oxygen atom. Now, there is a bond of some sort here which holds all these atoms together. Now look, hydrogen, hydrogen, 2 hydrogens, they've both got the same strength of bond to the oxygen atom that's in the middle. That's the thing that holds them together. Call it love, call it whatever you want. It's magnetism, it's gravity. I've got no idea what it really is because I'm not a physicist. But there's something that keeps this molecule together in that shape. Here it is again, look, H2O, 2 tied together to the oxygen atom in the middle. Now, oxygen is a very, very strange material. It's very happy to love in with anybody. It's almost incestuous. Look, it likes to go around on its own and join to itself. So you'll always find oxygen generally attached to itself in the form of O2. There is another form of oxygen called ozone, which you smell when you go down to the London Underground or you go to the seaside, and that's O3, and that's ozone. So here we've got the same molecule attached to itself. Okay, now oxygen will bond to all sorts of things very, very easily. So that's something to remember. But if you start taking a look at these structures, look at this one here. This is very open and wobbly, as I would like to call it. This one is pretty stiff because there's only one bond. These are quite stiff bonds here. But as you get more complex, some molecules have got very short, strong bonds between them, and other molecules have got very weak bonds between them. The strength of the bond between the atoms is totally variable depending on the material that you're working with. Let me give you a very silly example. You're at a birthday party and you've got jelly on the table. You've also got a birthday cake on the table. If you just gently bang on the edge of the table, which one will wobble? The answer is obvious. It's the jelly, because the jelly is obviously a very open structure like this. It's not a stiff structure and it very easily wobbles. It's a little mechanical analogy that I want you to remember when we move on a little bit further. Now, everything around you is made up of molecules and atoms, and you might not believe it, but they are all doing this, vibrating. Something that they didn't tell you when you were at school is that that vibration in a molecule or an atom is its temperature. Let me just put that a different way. If I can make a molecule vibrate faster, it's going to get hotter. You only imagine things getting hot, but what you don't see is that they're getting so hot that they're vibrating faster and faster and faster. And hang on, there is a limit to how much these bonds will stand. If you shake something hard enough, it will break. And that's what happens to these bonds when you shake them hard enough. So these two things, heat and vibration, are interchangeable. You've never imagined molecules vibrating and shaking themselves to pieces. You only see things burning. If we break these bonds here, for example, this oxygen will go off on its own and it will join with something else because it doesn't like being alone. So we get a chemical change when we shake these molecules to death, such that they self-destruct and they break apart. Our laser beam is generating a frequency at around about 28 trillion cycles a second. 28 trillion vibrations a second. Now that sounds unbelievable, but it just so happens that that is the frequency at which molecules and atoms can be stimulated to vibrate. So if we fire our laser beam at a piece of material, it will stimulate the molecules, make them hotter, or make them more energetic, to the point where they will eventually fly apart and change into a different material. So that's the way in which our laser actually works. Now we're going to jump around to another subject, light. I know we've just been dealing with light, but hang on, look, I've got a handful of light here at the moment. Can you see it? What colour is it? Well, look, I've got some radio waves in there, I've got some X-rays, I've got all sorts of waves in my hand. They're all part of the electromagnetic spectrum, and I've just got a handful of them. Where's the colour? I said to you that there's colour in that spectrum. And that colour comes from the sun, basically. It's white light. It's frequency of light that comes from the sun, and we see it around us all the time. It's invisible, but it's there. The problem with light is its energy. It's not anything really. It's photons, little packets of nothing that are energy floating in the air until they hit something. Now, look, a stone falling from the sky is not in the least bit dangerous until it hits you on the head. And then you know that it had energy. The same applies to light. What colour is that? You're going to say that's white. Well, not entirely true. That's all the colours of the rainbow there mixed up so that you can't see them. But that's what makes white light. All those colours. So, what colour is that? Yeah, it's a sort of a purpley colour. Yeah, but why? Why is that different to this piece of paper? There's every colour of the rainbow hitting both of those pieces of paper. With white paper, every colour is reflected back to your eye, and you still see it as white light. It wasn't white until the photons hit it and did something, and they made it reflect back to your eye, where you see it as all the colours of the rainbow mixed up as white. With this one, the only difference is that all the colours of the rainbow that are not mauve have been absorbed into that paper, and the only thing that's being transmitted back to your eye is the colour combination that makes mauve. So white is total reflection of all the light, all the white light, and we only call it white light because that's what you see. And in fact, look, there is no colour to this stuff here, which is light. Look, what colour is that? I know it's black. It's a colour. But it's only a colour because the light is hitting it. How much of that light has been reflected to your eye? How many colours of the rainbow can you see? The answer is none, because all of the light has been totally absorbed by that surface. There's none of it being reflected. It's a colour black. But in fact, it just means there's no light being reflected from it. Colour is a very interesting subject on its own, light, and how colour appears to us in our eye. We've only got sensitivity to that range of colours that I showed you on the electromagnetic spectrum. So you've got a little bit of a flavour now to why you're seeing black, white and colour. We only see the colour in light because of the non-absorption element of it. Now here's an interesting question, which you're going to say, well, look, hang on, this has nothing to do with air assist at all. Trust me, it's got everything to do with air assist that you've never even thought of. What colour is that? What's happening to the light? Basically, in this instance, there is no absorption of the light. It's not being absorbed, it's going right through. Look, you can see what's happening in the background. The light is passing right the way through this, and it's not taking any notice of it at all. Light is very strange. This is just water. I have to admit, I have put one drop of washing up liquid in there. Now, watch this. What colour is it now? And why? Okay, so it's turned white. And this is an analogue for what you're going to see in this video. I'm going to say that that is smoke in a bottle. It's slightly the wrong way round. What you've got in here are air bubbles which are playing with the light and reflecting it and making it white, remember, total reflection. When we see smoke in air and it's white, like steam is a good example, you know steam is still water, but it's micro droplets of water that are so small that they can actually float around in the air. But they are still micro raindrops, solid water droplets, very, very small. Now the important word there is solid. Now you remember what happens when light hits a solid surface? It vibrates the molecules. Let's go back to our pictures that we started the session off with and just take a look again to see if we can have a different perspective on what we saw in those pictures with these little bits of information that I've given you, these little science facts. The one thing I must state is that laser light can pass through air, gases, without any problems at all. It only wants to hit solid things, things that are molecules that make up solid items. You can clearly see that our laser beam here is passing through air. It's invisible here, but it must be doing something to something else here. Not only have we got our heating and our reheating of this crud that we're producing down here, we're squirting the material out from being solid into something very, very much more volumetric and gaseous. And then along the way, we're also producing, look, this plume of white stuff. Hang on, this is more white stuff. These are solid particles of whatever this is down here, but it's suspended in the air. That's why we can see them as white, just like fog or steam. Okay, so this is not just a gas. This is solid particles suspended in the air. And that's partially what we are probably reheating and reburning here. But the key thing that I'd like you to see in this picture is the way in which this white plume of smoke is going upwards. Then we'll move on to the next frame. It's starting to explode up here, a bit like an atomic cloud. The next frame we've virtually finished. Yes, we have. So look, the energy has ceased here as just a little teeny weeny reaction at the surface there. A continuation of the burning action that was stimulated by the laser beam, but the laser beam is no longer there. But what we've got, look, is our telltale puff of smoke that went straight up. So this is only 10 milliseconds of pulse, and in 10 milliseconds we have not converted a huge amount of material here. Some of this material has been burnt, and some of this material has been left as smoke. Now when we change to a different material, it will still be approximately the same, but it will be different because the material structure is different. The way in which the light reacts with those molecules on this surface, because they're different molecules to the molecules on this surface, there will be a different reaction. That's material that's turned into gas, and now it's being heated up by the incoming laser beam. And as we get further, look, you can see that the smoke is again developing out here. It's coming up like a little volcano, and it's going out. And there's nearly the end of the pulse now. And there it is. And look, you can see again, you've got our little plume of volcanic eruption here, and the smoke is drifting up. None of it's on the surface. we're going to double the pulse to 20 milliseconds. Again, look, we've got our plume of smoke which is coming up here as a little volcano. Something else is happening there now. We've lost our volcanic explosion. There's so much happening here that it's starting to come out sideways. We can see this rolling out sideways, look. You can even see the eddies in the smoke. Fascinating, isn't it? So let's look at the same thing with poplar plywood. Don't worry so much about this white stuff anymore because we know what that is. That's solid that's being converted into gas and then reheated. It's degrading the quality of your laser burn at the surface because it's having to heat up and do damage before it even gets to the surface. And now look what's happening. Look at the way in which it's exploding across the surface. Now I'm going to jump right the way from 20 milliseconds, which is what you've just seen, all the way up to 500 milliseconds now for a pulse. In half a second we should probably burn through this material completely. We're converting so much material it can't come up here quick enough. It's having to fly out sideways. Look at it. Oh my goodness me, look what we've done up here. Look at all the heat, all the fumes, look at all the energy that we're wasting up here burning up this gas. We're turning it from one form of gas here into another chemical which is flammable, and we're heating up that flammable chemical and making it catch fire. Now we'll do the same thing for poplar. Look at the way in which it's already flying out sideways, this gas. Yeah, look at the heat inside the wood. Can you see this illumination here? We've got a fire going on inside here. Smoke is not what it seems. Now, I keep coming back to this because look, this is the opposite way round. This is air bubbles in fluid. This is microfluid droplets in air. But these are solid, remember. So these will be affected by the laser beam if they're in the way. They will get reheated. They're solid particles. Look at the way in which this fog is moving across the surface. Look, we can see smoke coming out of the fibres here. Right, now just above my nozzle here, I've got a little tap. It's a ball valve, which is controlling my air assist airflow out of this nozzle. Now this nozzle has got a big hole in it, so there's not a great deal of directed airflow. It is a strange airflow coming out of here. It'll be totally chaotic. And there we go, you can hear it. Now that is my pulsing, silly little Chinese air pump that they supplied with the machine 6 years ago. We'll do the same test again with a 500 millisecond pulse. Immediately, one thing I think you can see is the shape of the smoke cone. Look, it's no longer emanating up this way as a volcano would do, explosively upwards. Look, we've got smoke which is being blown down. This smoke that would normally be wanting to go up is being forced down onto the work by the air assist that's coming out of this nozzle. And look, it's blowing out the side here, right across the work. The actual fumes themselves this time are not going as far up towards the nozzle because we've got the air that's driving this, let's call it gas, before it burns, downwards. But you can clearly see the path of the laser beam itself. It's straight down and it's through the centre of the nozzle. Okay, so now I'm going to do a cut with the same power but away from the camera so that we can see what happens. And again, you'll notice we're getting air blown everywhere sideways. But if you look carefully, you'll see that there isn't much happening out this side, but a lot of the air is blowing out this way. We've got some sort of bias happening. Maybe it's because of this air assist direction here, but we've definitely got a bias to the left with this smoke if you watch. Can you see that puff of smoke going out left? Virtually nothing coming out here to the right. And now we do exactly the same thing, but this time we do it with the MDF. Again, look, the smoke cone is going this way. But now it's underway. Oh, what was that? That was interesting. Wow. I mean, that wasn't a piece of my hair. Look, there's a little stringy thing that's happened in the gas. I've got no idea what that could be. But you can see the way in which the air assist is keeping the flame down away from the nozzle this time. It's actually protecting the lens nicely. Right, so here we are on the plywood. We're going to run the same line away from the camera, but this time with no air assist. And wow. Oh my goodness me. Now you'll notice with no air assist how all the smoke is going upwards. There's nothing going down anywhere near the work. So let's stop there because it's enough. Now we run the same test on MDF with no air assist. I'm almost frightened to watch this. Now you remember we saw that little worm coming out the flame when we were cutting MDF. Here they are again, look. Again, you'll notice the smoke is going away from the cut. We're not getting anything around the side of the cut at all. Wow! And what's happened now, this gas has been ignited by the laser beam itself now. It's obviously got hot enough and it's changed its composition where it's burning the gases. So the gases are actually being consumed now in a flame tail that's coming out towards us behind the cut. It's not actually interfering with the nozzle itself. Look, we've got virtually no smoke now because all the smoke is being consumed in this fire here. And there we go, look, no smoke at all. Now this is the poplar plywood. Neither of these cuts are going right the way through. So they're both blind cuts, which means that all the fumes that are produced have to come upwards. Now in this case, the fumes coming upwards have been blown back down with a left biased air assist. And that's why we've got this here. It's not on the right hand side, it's here on the left. When we had no air assist, we've got a nice clean cut because as I pointed out to you, all the fumes were drifting upwards. They weren't going anywhere near the work. And we had exactly the same results on the MDF. Look at this super clean cut here. We haven't even got a start point because all the fumes were being burnt. I've now put the work up onto spacers, 10mm spacers, to get it off the deck so that we don't get those marks on the back. And we're going to attempt through cut. So we've got plenty of power there. We're going through very nicely. So the cut was through. Something is happening here because we're not getting air flowing through the cut. We're still getting some crud here on the left hand side. So we must be getting some upwash of fumes. When we move along this cut, some of the cut is deep, but there will always be a piece of cut that is right on the surface because remember, we're cutting this slot molecule by molecule, and the first molecules that are cut and disturbed are those on the surface. And there's nowhere for the fumes to go on the surface. And so unless we get some well-directed airflow to suck the fumes down into the cut and out the bottom of the cut, we're going to get some debris on the surface here. Now again, we've got this left biased debris because of the airflow from our nozzle. So look, here's our nozzle. We've got about a 6mm hole in the end. It's a huge hole. So here we have what I would call a cutting nozzle. It's got about a 2 or 2.5mm diameter hole in the end of the nozzle. So this won't produce a waft of air. It will produce a jet of air. Do we want a jet of air? Listen to the sound difference. First of all, because it's restricted, you can hardly hear the pulsing. It's another piece of physics which I'm not going to go into. Let's just see what difference this has. Remember that smoke that is busy absorbing your energy because it's coming up? We're pushing the smoke down as fast as it's being produced. We're not allowing it to go near the raw, lovely, new, naked laser beam. It's being blown away from the laser beam. And there we go, a lovely clean cut. And the bottom, it's not what I would class as a cut. I know it is a cut, it would come through. But basically, if we take a look at the difference between the top and the bottom, effectively what we've got a V cut, wide at the top, very narrow at the bottom. Now what that's going to do is going to choke the airflow through the cut. It's not going to allow very much airflow through the cut. So we're basically, although we've got what many people would regard as a good through cut, I don't regard that as a proper good quality cut. So I'm going to take that down to about 7. We'll run another cut beside it so that we can compare them. And now we've got a cut which is much the same on the top as it is on the bottom. And that means we've basically got a parallel cut through which the air can flow and it does not get choked. I've got my solid table on now, which is a piece of nice cold steel, and I've got some 3mm spacers and some 3mm HDF. Now I'm going to do the same thing that I've just been doing. We're going to run a line away from the camera. Okay, so two things I'm going to make you note. Number one, if you catch it in the light, you can just see a shiny edge to it. So there's some sort of overrun, there's some sort of painting that's taking place along the edge of the cut. Now the back of the cut is not bad, but look what we've got here. Look at this. That's what would normally go onto the surface of your work. That's the tar that's being generated in those fumes that I talk about. That's the liquid content of that white smoke. I've just condensed it onto this very cold surface. So if you've got any doubt as to what that brown stuff is on the surface of your material, it's not burning. It's recondensed tar. I'll just clean it off with a little teeny weeny bit of acetone. Now put it on 10mm spacers to keep it away from the surface, because although I got a reasonable cut through, I got terrible back reflection off of this base plate. So we're still getting some reflection off the back plate, so I've got to go even further away. On the back, I've got rid of all the reflection. On the front, I've got rid of all but just the merest hint of that marking that I was talking about, because most of the air is going through. And I say most of the air because look, again, we've got a much smaller cut on the back than we have on the top. And that means I've got a tapered cut and I'm choking the airflow through the cut. So I'm running too fast. It's getting better, as you can see. We've got a much wider cut at the bottom now. And again, I've got a lovely clean mark-free cut on the top. Okay, so here I've got a piece of 3mm birch plywood. I'm going to use the same settings at the moment, the same speed, but I know I should be able to go a lot faster. But let's just run it at this very slow speed to start with. And we've got a very nice clean cut on top and the same thickness of cut underneath. So let's change to quite a fast speed now, 30mm a second. Two things you'll note. First of all, the thickness of the line is just about through. It's a just cut. But look what's happened to the surface. There is a hint on here of browning around the edge because I'm not allowing the air to pass cleanly through the cut. I'm getting some backwash from the cut itself. So I'm running too fast. Okay, so we're now getting a better cut on the back, but it's still not a full width cut. But we've virtually got rid of all the marking on the surface. We've got airflow through the cut. A little bit slower. And we've got a lovely clean cut on the top. And it's becoming a half decent cut underneath here. And that looks like a very nice cut. No marks on the top. One little burn mark here on the outside where we always get a burn mark because that's where you start. You're blowing fumes upwards because there is no hole through which to blow the fumes. I've got a nice cut, clean cut there. I could say that there's 3 psi in that cut, but it's not 3 psi. I've driven a certain amount of flow rate through here. Look, you can hear the flow as it passes by my finger. I can tell you what the flow rate is through my nozzle because I've got a little flow meter here. So at the moment I can tell you that I've got roughly maybe 10 or 11 litres a minute passing out of that nozzle. So now I've restricted that flow rate to 8 litres a minute through my ball valve. The problem is we can't see the flow that's happening out of this nozzle. It feels very gentle now, it's less of a jet. But let's just have a look and see what it looks like. That's still a pretty unstable flow. So let me try and choke it off a little bit more. Look at that, we've got a lovely stable flow there, and that's virtually no flow. Let's try and see what that's like as an air assist flow. I wouldn't say it's laminar flow, but as you can see, it's not opening up to a very wide flow pattern. Well, it still cut the square, but it's made a bit of a mess of it. Look, we've got burns at each corner where it's slowed down. And it has sort of left marks on the surface. So we do need more air assist than that. Let's find out where we've got to go to. Well, I've got a pretty clean cut there at whatever flow rate that is. And the answer is about 7 litres a minute. And that's using one of these little pumps, which is capable of delivering maybe 40 litres a minute at 3 psi. It's not controlled by the psi, it's now controlled by the restriction that I've got on my restrictor here. I'm controlling a flow rate. I'm not controlling a pressure. Pressure across an orifice develops a flow rate. The bigger the pressure difference across an orifice, the more flow I will be able to deliver across that orifice. If I leave this ball valve set exactly like it is and I increase the pressure in the system, I will increase the flow rate through the nozzle. So look, I've increased the flow rate to 5 litres a minute. What's it done to my flow pattern? As you can see, I still have got a fairly stable flow pattern. Let me see if I drop this nozzle down a little bit more. Well, it's becoming a little bit unstable, but it's still a fairly small flow footprint, as you can see. you'll see what happens to that footprint as I increase the flow rate. Right, we're now into one of my dodgy diagrams. Look, I've got a nozzle here, an orifice, which has got 1 psi inside the system coming from a pump, and I've got 0 psi on the outside because that's what is just here, nothing, atmospheric pressure. So what will happen is the air will build up through this nozzle, and it won't flow very evenly because this is a sharp-edged orifice, but it will come out of here and it will probably take a shape something like this, and then it will gradually do this because at 1 psi there isn't a huge tendency for that air to want to expand outwards. If, as some people claim, they're using about 30 psi, then what's going to happen is 30 psi across this orifice is immediately going to do this. It's going to climb out here and it's going to expand as rapidly as it can. We've got a kerf down here which is 0.2 millimeters wide. How much of that 30 psi airflow, and because we're not talking about psi, we're actually forcing an airflow through this orifice. 30 psi is what's causing the airflow, and it will cause a very rapid airflow through there at high velocity, but as soon as that air gets out of this chamber at high pressure, it's going to act just like a balloon bursting. It's going to pop and it's going to expand rapidly. How much of that air is going to find its way down this 0.2 wide kerf? Most of it's going to go across the surface here like this, and it's not really going to do much to help get air through there. The right approach is to try and get a nozzle with a small orifice like this and get it as close as possible to the work. And you don't need high pressure, as I've demonstrated to you. 2-3 psi, even pulsing 2-3 psi. But because what happens is this pulsing action that's taking place with this pump is being met with this restriction here. So what we've got basically like an accumulator in the system. The system is actually damping out the pulses when we've got a restriction right at the end of the system. When I've got an open system here, as I had when it was 6 millimeters, you could hear the pump pulsing. Airflow was coming out gently, but it was coming out in a sort of a bit of a random fashion like this. It wasn't high velocity, high expanding gas. It was fairly low velocity, low expanding. There was a definite bias to the airflow, and I think that's because of the way in which the air comes in from one side. It's not something that I've really noticed before, but I did notice it when I watched the video. Am I talking crap? It's getting a bit late and cold in this workshop tonight, so maybe tomorrow, ta-da, we'll get that little beastie there working. Air assist on its own is great, but it needs something else as well to help it, and that's extraction. I've been running this machine without extraction on it, so you can see the way in which the smoke goes up in the air, especially during engraving, because one of the things you don't want to do during engraving, as I've demonstrated to you, is to blow the fumes back down onto your work, because that's how you paint them brown. What we try to do is to get the smoke to come up in the air, but coming up in the air only fills your cabinet. What we've really got to do is to manage the airflow through your machine so that it carries the smoke away quickly. Now, I've arranged it on this machine with a closed-in steel bed. Okay, there's little teeny-weeny gaps around the outside, but in essence, what I've got extraction duct along the back there, and virtually no places around the edge to extract air from. You will notice on the corner of my door I've got stops. Although I've got some holes here which I've blocked off with tape, I want a sheet of air to be drawn in to my machine and pass rapidly across the engraving surface. If you're cutting, it really could do with going underneath the cut to extract the fumes just as quickly, because you saw yesterday what happens when the fumes condense on this surface. So now we're looking underneath the door at the nozzle, and we'll see what happens to the smoke this time when I turn my extract system on. I think you'll agree that that is substantially better than anything I've achieved before. And listen, I've got air assist on as well. Based on what I've just seen in my video, I've modified the air assist. I've still got my short engraving nozzle on here with a big hole in it, but look what I'm doing this time. I've got my air assist disconnected from here. I'm not blowing it through the nozzle. I've got it connected to a little fishtail, and I'm blowing it across the nozzle. And that air, if I just turn it around slightly, is now going to assist my managed airflow, which comes through just here and goes towards the back of the machine, and it's going to drive the smoke backwards, but it's also going to protect the lens without driving any of the air down onto the work. Let's look at the fumes being drawn away with this managed airflow and this different air assist for engraving. Not a hint of browning anywhere. The problem that you're going to have when you're doing engraving and cutting on the same job, what compromise do you make? Because there are very, very specific conditions that you need for engraving and completely opposite conditions for cutting. As you can see, I've just made this out of a couple of pieces of perspex, but I might have to make something a little bit more permanent out of aluminium or something to do that job. Now, what I haven't done at the moment is done any scan engraving. Wow, not a hint of brown anywhere on there, which is amazing for MDF. I've purposely taken the protective film off a piece of acrylic to do exactly the same test, because under normal circumstances I've never been able to engrave a piece of acrylic without leaving debris everywhere. Well, that looks pretty amazing, to be honest. I mean, that is so clean. I mean, and also the other telltale thing that I only get when I do very, very faint engraving, and this is not faint engraving, is look, see the settled acrylic condensate? It's already cooled and it's condensed as a powder. It's no longer bonding to the surface. Look, it just wipes off. Not only am I demonstrating to you, I'm discovering things that I hadn't really discovered before. I showed you that compressor that I had and said we'd get on and do some quick experiments with it. Now, the main reason why I'm told that people want to use these shock compressors is because it gives them deeper cutting, faster cutting. My recent work has made me understand exactly how lenses work, and what you see here is me just about to cut a piece of hardwood 26mm thick using only 60 watts and a 2.5-inch gallium arsenide lens used the wrong way round, flat side up. This is a quick edit of a video I did a couple of months ago. I set my lens a millimetre off the surface, and I'm only using my silly little Chinese pulsing pump. And look, it's cutting right through it. It's just hanging on by that last little bit at the end, which may have been a knot. And look how square and clean the cut is. Do I need to cut any deeper than 26mm? This is the ultimate test. Will extra air assist allow me to cut that faster? If it does, I've got some serious thinking to do, because I've been down this path before when I very first got my laser machine. I came from a background of metal cutting lasers, where you need very, very high pressure gases to do the cutting. And the first thing I did was to throw away this little Chinese pump, put my shock compressor on there with a regulator. Within about 3 weeks, I'd destroyed 2 lenses. And let me explain why. The physics of using a shock compressor don't compute. Now, I learnt my lesson the hard way. I'm using my noisy old piston-driven shock compressor. That was supplying about 80 or 90 psi into a reservoir. It was feeding down a 6mm bore pipe, and that area is about 28 square millimetres. Now, it was feeding into a fitting which was in the nozzle, which was only 2.5mm bore. And then the outlet of my nozzle at that stage was a big 4mm orifice, 13 square millimeters. Now we'll add a bit more detail to this picture to explain what my real problem turned out to be. Now this was towards the end of the summer months when I first got my machine, and here in the UK we don't get incredibly high humidity. I mean, it might get to 60% sometimes, but most of the time it's in the 50% region, pretty stable. Okay, and on a very hot day we might get up to 30 degrees C atmospheric temperature. Most of the time it's a lot less than that. So we've got high humidity air coming in at 30 degrees C, say, into the pump. Now the pump, when you compress air, it heats up a lot. When the air was pumped up to 85 psi, I didn't measure it, but I can tell you it's at least 80 degrees C that air is being pumped into that reservoir. Air has got a very interesting property. It's a bit like a sponge. The higher the air temperature, the more water it can hold. Cool it down and it throws that water away and rains. You can look up the tables for things like relative humidity, dew point. These are all factors that happen to come into play with this scenario. If you leave your compressor overnight, for example, and it all cools down and that water rains inside your reservoir. And so there will always be, in most reservoirs, because people don't have the discipline of emptying them every day before they start work, you will have a little pool of water sitting in the bottom of your reservoir. So once you start the day and you start compressing air at 80 degrees C, remember, when air gets hot, it loves to suck in more water. And that air is sitting over a big puddle of water. So now you pumped in air at relative humidity for the atmosphere, but all of a sudden it becomes even more humid rich because it's hot. And then it flows down your system at, and some people are claiming 30 psi. And I was playing around with those sorts of numbers as well. Because at the end of the day, you pump a lot of pressure down here, and what we find is that pressure, to force lots of air out of here, we're having to put a large pressure difference across this restriction here. Remember back to this here, look. We were able to pump air down here easily, but it's not going anywhere because it gets restricted by this 2.5mm bore. And the only way you can push lots of air through that 2.5mm bore is to have a big pressure difference between the inside and the outside of that tube. So what's going to happen, it goes from 30 psi to almost zero, but not quite zero. And as it does so, it expands. And as it expands, it then has to come out of this orifice. Again, we're talking about flow. So it flows out of this orifice with only maybe half a psi difference between here and here, because this is so big in relation to this. This is the major pressure drop. And as pressure drops and air expands rapidly in this chamber here, it cools down, because it does the opposite of when you compress it. And it drops below the dew point of this supersaturated moist air that you've just supplied to that point there. And it's now producing condensation in this area here. I'll bring you back to something we spoke about earlier. Steam, solid particles. Laser beam loves to hit solid particles. This is water vapour. These are solid particles of water, little micro droplets, but they will be reheated up in here by the laser beam. And as they heat up, they will drift towards the top and sit on the face of the lens. And there will be eventually some crud that actually bakes onto the face of that lens, because we've got a little oven in here, a little superheated water oven. And that's basically what happened to my lenses. I cooked crud onto the bottom face of my lens, 2 of them, before I worked out what was going on. And at that point, I took my compressor off And for the last 6 years, I've only ever used these silly little Chinese 3 psi compressors. Now, if you've only got air pumped up to 3 psi, it's never going to get hot. And if you use it as you compress it, it's never going to sit over any water. So that's why I use this silly little Chinese pump. It works admirably. Can I just point out, I've just cut 26mm thick hardwood using only 3 psi air. Wrong. I've used about 8 or 9 litres of flow through my nozzle to cut that. Free flowing air into my nozzle and a restriction right at the end of the flow path. And so I had 3 psi in here and 0 psi here. The difference between 3 psi and 0 psi is not enough to cause it to rain. And even if it did rain, it would be raining outside the nozzle, not inside the nozzle. I mean, that's a very, very scanty, brief physics lesson of what's going on in this system. So that curve is only 0.2mm wide, and that is why you saw me on this video putting my nozzle within 1mm of that cut to get the most efficient use of the air flow through that nozzle. That's all I'm going to say. It's your choice, it's your money, they're your lenses. But it depends on what part of the world you're in. This may be a bigger problem to you in certain parts of the world because of the difference in the humidity. And I've hooked this up to my machine and I've set it to 2 bar on the regulator, 28 psi. So I've set the flow rate to about 7 litres a minute, which is what my normal Chinese pump will be able to deliver easily. The pressure in the system doesn't matter at all. There's 28 psi there, but what I've just done is regulated this flow through here. Goodness me. You'll understand why I say goodness me in a minute. To 8 litres a minute, as you've just seen. Now, this pump, this compressor is supposed to be able to work with something like about 150 litres a minute. Now that's 20 times more than what I'm putting through here. But of course, that 150 litres a minute is 150 litres of uncompressed air. This little compressor, it's not small, as you can see, is struggling to keep up with even that low flow. What we'll do is just pop this down to within about 1mm of the work surface, which is where it's focused, so that I can get the maximum amount of airflow through the cut. Some 9.5mm MDF here, and what I'm going to do is start off the edge of the cut, and I'm going to run this first of all at full power. Speed to about 5mm a second would be more reasonable for this. Not worried about what it looks like on the top. What we're worried about is what's coming through the bottom. It's just about making it through. Do you see what I mean about that pump? Look, it just keeps on and off, even though I've got a very, very low flow passing through there. Now, if the theory is right, I mean, greater pressure is only going to give me more flow. So I've opened up the valve now, so we're running at about 15 litres a minute. That's twice as much flow. The one on the left has got twice as much airflow as the one on the right. Has it made any difference to the depth of the cut? If the depth of the cut was any deeper, the cut at the bottom would be wider. The answer is no. The cut depth is determined by the lens itself. It doesn't require a sledgehammer to crack a nut. Now I've doubled the flow rate. This is never going to turn off. It's going to struggle to keep up. I don't want to hold that for very long. Okay, so I put my little pump back on. You can just about hear it making the noise in the background if you really listen. And I've now got the valve fully open. Maximum flow rate, what, about 12 litres a minute? That's 50% more than I think I need. And that's out of a little Chinese pump that consumes 60 watts, as opposed to this beast here, which consumes 750 watts and still can't keep up. Well, I did warn you that air assist is not the little throwaway subject that many people think it is. I'm going to leave you with this summary here. You can put your machine on pause and read it at your own leisure. Well, thanks again for your time and patience, and perhaps next time we'll get back onto the new machine again.